Lesson 3.4, and we are going to be solving equations using logarithmic expressions. The first thing that we're going to do is just kind of look at two options when we have for solving logarithms. One option is going to be using your graphing utility, and then the other option is going to be solving algebraically. So right now what I would like you to do is go ahead and enter both of these functions here, the 2 to the negative x plus 1 minus 3, you want to include parentheses around your exponent. Enter that into y1 and enter the 13 into y2, and then you're going to do second calculate and find their intersection. And when you do that, you're going to find that the ordered pair is going to give you where they cross each other, where both of these graphs cross, and you're going to get an x value and a y value. The x value is going to be our solution, so whatever x equals, and the y value is obviously that 13 there. But you should get, for your solution, you are going to get negative 3. Now I'm going to show you how we can get that algebraically. Well, you're going to set the 13 then equal to the 2 to the negative x plus 1 minus 3. This is how we solve when we have either exponents or logarithms. You're going to add the 13 over, that's 16 equals 2 to the negative x plus 1. And here now it's time to turn this power right here into a logarithm. So it's log base 2, the 2 comes from the base of your exponent, of 16 equals negative x plus 1. That is, log base 2 of 16 is 4. And as you can see here, we can just continue to solve that. 3 equals negative x, so x equals negative 3. All right, that's your solution to this equation. All right, you can see here that we've got a lot of different ways that we can solve. There will be times when you can solve on your own and you don't have to actually go through any procedures, like in this first example, 7 to what power is 1 over 49? Well, we can go ahead and look at that as saying that, well, x must be equal to negative 2. An alternate method would be to write your log base 7 of 1/49 and have it equal x. Either way, you're going to still get x is equal to negative 2. All right, for letter B, e to what power is 0? What x power can I have in there and as an exponent to give you 0? There's none. There's no solution here. Now I can show you by writing it as a logarithm. So log with base e is natural log of 0 equals x. Log is undefined at 0. So no solution for number 2. We can't take the natural log of 0. All right, letter C. Here's one method that we can do. You can move the natural log of 2 to the other side. You have natural log of x equals natural log of 2. Therefore, x must equal 2. Okay, so we're solving our equations. And finally, for letter D here, what base with a power of 2, exponent of 2, will give you 25? The answer is 5, but let me show you how. You do x to the second equals 25. X would equal plus or minus 5. However, you can't have a base that's negative, so our conclusion is just 5, not the minus. So there's a little bit of experience there with solving these logarithm equations. We're going to continue this and see how we can use some of our rules to simplify or solve. This says simplify the expression. Well, what I do know is that this 2x is an exponent and I can put it in front. So negative 1 plus 2x ln of e. ln of e, this expression is equivalent to 1. So we've got negative 1 plus 2x. All right, we also have another expression here that represents what we call an inverse. And in this inverse, you have base e of, so you have base e, if I'm doing that as ln of e, of, and the of number is what we don't know, equals the exponent ln of x to the third. So this concludes that this expression right here is equal to that x to the third. So we just have negative 8 plus x to the third. That's it. That is the simplified version here. These were inverses, so your ln of e cancels and your e to the ln cancels, and you're left with just those exponents. All right, so we're going to get a little bit deeper here into our solving when we can't necessarily do them on our own. On this first one here, your goal would be to try to isolate this e to the 2x. We can do that by adding the 3 over to the other side. 4e to the 2x equals 5. And then we can divide by 4, so e to the 2x equals 1.25. Now to conclude, what our next step here would be to, in order to get the 2x away from the exponent, you're going to write it as a logarithm. Since my e is a base, then I'm using natural log of 1.25. You're just rewriting this in the log form, equals 2x. When you solve this, you're going to divide by 2, and you're going to type this in your calculator. Natural log of 1.25 divided by 2, and that should give you approximately 0.11. So that's the solution to that equation. You're going to see that we have some similar processes here with the second one. I want to try to isolate this power of 3, so I'm going to add 4 over to the other side. Add the 4 over, you get 11 plus 4, which is 15. We're going to divide by 2, so that equals 7.5. You still have your exponent. In order to solve this, you have to write it in logarithms. Your logarithm would be log base 3 of 7.5 equals 2t minus 5. When you solve this, you're going to take your log base 3 of 7.5, you would add 5 to it, which is going to get rid of this 5, and then you would end up dividing all of it by 2, which will then isolate your t. So t will equal, in this case, 3.417. You're going to have to use your change of base formula in order to evaluate the log base 3 of 7.5. All right, looking at this next problem here, you're going to want to recognize that you've got one term in the front, 2 terms in the middle, 3 terms here on the end. You also see the exponents are decreasing and then decreasing again. It's a quadratic form, and in order for us to solve quadratics, we will factor. And these can be factored. You've got factors of 2, so 1 and 2. And you've got factors of e to the 2x. That's going to be e to the x times e to the x. And your signs are both subtraction. While solving quadratics, your process or your intention is then that you're going to set each one of those expressions that you get, you set them equal to 0, and you solve. So this would be e to the x equals 1, which concludes natural log of 1 is equal to x. So that first solution we get is 0. Okay, I'm going to go through this same process, but now I'm going to use my second binomial that we have there. So first solution is 0. Second solution, you're going to do e to the x equals 2, which is ln of 2 equals x, and then the natural log of 2 is 0.69. So those are your solutions. X equals that, 0 and 0.69. You can see here in each of these I had to write my powers as logarithms in order to solve. Moving on to example 5, I've got a couple more equations here that we're going to solve. For letter A here, you've got log base 3 of an expression and log base 3 of another expression that it's equal to. Well, what we can conclude is that these two are equal to each other. So if you have 5x minus 1 equal to x plus 7, you solve that. So we know that's 4x minus 1 is equal to 7, or 4x is equal to 8, x is equal to 2. All right, letter B. First thing that I'm going to do is I'm going to go ahead and divide by 2. And so that will give you 2. And then your next process will be to go ahead and take this logarithm and write it as an exponent. It would be 5 to the second equals 3x. And now your goal is to just solve this. So 25 equals 3x. X equals 25 thirds. And you can keep it like that. Otherwise, you're going to leave it as a repeating decimal. We don't want that. All right, on your next problem, you are going to want to, we're going to talk about this checking for extraneous solutions here. But in this problem, your goal is going to want to try to combine these natural logs here and use some of your condensing rules. And so we will take care of that here in a second. All right, so again, because we have more than one natural log here on the left side, we're going to do the condensing rule, where because of the addition, we're going to write this as x minus 2 times 2x minus 3. So all of that is in the natural log. And then on the right side here, this is a power of 2, so it's natural log of x squared. All right, you've got natural log on the left, natural log on the right, and we're going to now take this and do x minus 2 times 2x minus 3, set it equal to x squared. This is a quadratic, and we solve quadratics by setting everything equal to 0. So I'm going to go ahead and FOIL this out. X squared minus 3x minus 4x plus 6 equals x squared. Combining all of my like terms, I have x, this would be 2x squared in the front, but combining all of my like terms and moving the x squared over, I have x squared minus 7x plus 6. You'd want to look at this quadratic and see, for solving purposes, is it able to be factored? Can we factor this, set it equal to 0? You can. It'd be x minus 6 and an x minus 1. So your solutions at this point in time are 6 and 1, or you need to look for extraneous solutions. So here's what that means. You cannot take the log or natural log of something that's negative. Well, if I put 6 in, that's natural log of 4, that's okay. Natural log of 12 minus 3, 9, and natural log of 6, that is okay. But if I put 1 in here, you have natural log of negative 1. So that is an error. You can't do that. You cannot put 1 in. So that's extraneous. So your only solution to this one is 6. 6 is the solution. You need to exclude the 1. All right, on this problem here, I'm going to want you to approximate the solution. There are going to be some equations that you simply cannot solve on your own, so you have to use the calculator. You're going to put ln of x into y1. And then I want you to put x squared minus 2 in for y2, and I want you to graph it, and I need it for you to see where they cross each other. And your graph is going to look something like this. Just to give you an idea if you're graphing it right. You want to pause the video and do that, you can. And it's going to look something like this. It's not exact, I'm just giving you an idea. So you need to find both of these intersections. And you can do that by doing the second calculate intersect, and you want to calculate both of them. You want to get your two solutions that you will get is going to be 0.14 and 1.56. So sometimes you will use your calculator to graph, and you just have to find out where your graphs are going to cross each other, and those are considered to be the solutions. All right, we're finally now going to be looking at an application problem, and so we can see where some of this solving and using logarithms might occur. You have deposited $500 into an account that pays 6 3/4 interest. Compounded continuously, how long will it take for your money to double? Well, this is how we find continuous interest. A equals principal times e to the RT. It's the PERT equation. So here's what I know. We have $500. Your rate is 0.0675. We're supposed to find how long, t, for it to double. Doubling would be 1,000. So you've got 2 divided by 500. So 2 equals e 0.0675 t. You write this in logarithms. Your logarithms would be log with a base of 2. Excuse me, not with base 2. It'd be the natural log of base e of 2 equals 0.0675 t. Divide by 0.0675 t, 0.0675 both sides, and your t then would equal how long it would take, and in this case you should get approximately 10.3 years. That's how long it would take for you to double your money, again, at that percent. All right, we got one more problem left, and you are going to do this in your calculator. For selected years of 1980 to 2000, the average salary Y in thousands of dollars for public school teachers for the year 5 can be modeled by the equation. Here's what you're going to put into Y1. You can use the X for your T here, and you're going to set your domain from 10 to 30. You're going to graph it and set your window up, and you can do zoom fit, and that will give you a nice window. T equals 10 represents 1980, and it says during which year did the average salary for public school teachers reach $40,000? So you can do Y sub 2 equals 40, and that will help you with your graphing, and then what you can do is calculate where they intersect, and that should give you a result. You can pause at this point in time and graph it and find it. You should be getting X equals about 28, so 28 years. If 1980 is when X is 10, then this would be 1998. That's the year that we're looking for. All right, that concludes the section for today, and this is the assignment.